here in terms of similarity transformations. But guys, the thing that we need to know in terms of similarity, you just need to know same shape, different size. I have William Byron's 1/64 scale race car. Now, if we had the real race car, you said they're similar. Boy, if we had the real race car, we'd be in that north parking lot burning one down too. Oh my gosh. Can you imagine 700, 800 horsepower out there and just burning some cookies out in the north parking lot? You think the coppers would get mad at me up there? Do you think they'd come in? But you know what? They probably couldn't catch me if I had his car. So who cares, right? Wouldn't that be awesome? Okay. All right, guys, let's get into example one. Okay, this says graph line segment AB with what endpoints, kids? 12, -6, and what? Okay, so 12 might go off paper just a tick here. So let's go ahead and try and figure out where 12 would be. We're going to go to 12, -6. So right 12 and down 6. There's be 11, 12, and then down 6. You guys agree that 12, -6 might be right about, oh, maybe here? Okay, I'm going to call that point A. You all agree with that? Where did point B end up at? Where do they want point B at? Does it say 0, -3? Okay, so 0, -3 would be right here. Do you guys want a ruler? Let me get you a ruler. Hello? Yeah. Okay. I might be able to, yeah, and if they have an issue, I listen, it's just a seventh grade game, I could probably run it too. So, sound good? All right, sounds good. You bet. All right, friends. Let's get the ruler to you here. Sorry about that. All right, friends, let's roll. Go ahead and draw your line segment. I'm going to do the same thing here. All right, I've got my line segment drawn there, okay? Now, it says, first thing you're going to do is reflect it in which axis, kids? Y-axis. That's this vertical line right here, okay? It's this vertical line right here. We're going to reflect it over that line, all right? So, guys, is this point B going to move at all if I reflect on that line? Okay. Well, guys, how many units to the right of the y-axis is A? 12 to the right. So A prime would fall 12 to the left, wouldn't it? So let's go ahead and draw this right here. Let's label this. Let's do the reflection first. So this A is going to move over to -12, -3, right? So let me get a different color here. So let's see. This would be -10, -11, -12 would be right out here, just off that graph a little bit. I'm going to call that A prime. And then B, is B even going to move? Kids, if I fold right on the y-axis, you would say, nope, not moving. Okay. So guys, all I've done so far is taken that line and done what? We reflected it over the y-axis, didn't we? Oh, I think I got the wrong point, didn't I? No. I've got it, don't I? Why does that look so off to me? Is it right, kids? Did they do that? I think it looks right. Maybe it's because I don't know. Maybe it should have been a little higher, maybe. I don't know. Does that look good, guys? Are you sure? Okay, so that first thing was the reflection, wasn't it, kids? Okay. Now what do we have to do? Okay, well, guys, where is A prime at right now? What coordinate is A prime at right now? Okay, and then where's B prime at? Still at what? Okay, now what we're going to do, that was the first one. That was the first move to get to A prime and B prime. Okay, we reflected. All right. Now what's it say to do, kids? Dilate, right? Okay, so we're going to take all of these coordinates times what value? 1/3. Kids, did the reflection necessarily change the size of this at all, or did it keep the same size? Is that length still the same? Kept the same size. Reflection's not going to change the size. What's going to end up changing our size right now? Okay, let's go find our new points. So now let's dilate these in. We'll call these new points A double prime and B double prime, because that's our second move. Kids, what's 1/3 of all these values up here? What would -12, -6 turn into if we took 1/3 of all that stuff? Yep, -4, comma, -2, and B double prime would turn into what? Okay, so let's plot those. I'm going to use a different color here. Let's just go, how about yellow? Okay, so our points are left 4 and down 2. This would be B double prime. Okay, and then the next one will be 0, -1, which is right here. And that would be A double prime. And we'll go up there and draw my line. Kids, what's true about the, is it still a line segment? But what's true about the size now? Same or different? Very different. Okay. And that blue line is what we get after reflecting over the y-axis and then dilating by what scale factor? 1/3. Okay. And this would be considered a similarity transformation. Guys, we took this line, we did some things to it, but in the end, the line didn't stay the same length. It actually did what? Okay, and that's why it's similar. It's the same shape, but it's a different size now. Okay. All right, let's see what we've got. Is that it on page 1? Wow, this is not going to take long today. Okay. All right, let's talk about example 2, describing a similarity transformation. Okay. It says, describe a similarity transformation that maps this trapezoid WXYZ to trapezoid PQRS. Well, you tell me, kids. We're going from the blue one to the green one. Okay. Now, are we going to have to change size at some point? Are they the same size? The blue trapezoid, the green trapezoid, are they the same size? No. So at some point, we're going to have to dilate this. We're going to have to enlarge it, right? Okay. But how do you make this blue line completely fall on the green line? What may have to do to it first? Flip it over. Okay, let's just see what a flip looks like first. Okay. Guys, let's flip it over. Maybe flip over which axis you thinking? Okay, let's do that. Let's say flip over the x-axis. Okay, let's just kind of sketch what a flip over the x-axis would look like. Guys, how far above the x-axis is W? This point W right here, how far above the x-axis is it? So when I flip it, W would fall where? Okay, so wouldn't W fall right here, kids? Agree with that? Where would X fall? Wouldn't that fall one below as well? And then wouldn't your Y and Z fall one above? So when I flip this, ooh, kids, look. When I flip this, does it at least kind of get me going in the right direction, the way the green one's going? Okay. All right. Guys, I'll just tell you y prime fell right here. All right. Guys, go from the origin to y prime. What's the distance? Origin to y prime. What's the distance up there? Actually, it's just from origin to 1 unit. How about the origin to this point r up here? Doesn't it look like this needs to fall up here? To make it bigger now, guys. To go from the origin to r, that point where y prime would match up with r after flipping, what's that distance? Okay. So how big of a scale factor are we going to have to dilate this black trapezoid to? Okay. So it looks like a flip over the x-axis and then dilate by a scale factor of what? What was the scale factor? Can I abbreviate scale factor as SF? Okay, does everybody see what I'm doing there? Another way to look at it would be this. Guys, what's the distance down here? I'm going to look at just this side right here. What's this distance after I flipped it right there? How many units is that distance? That distance is 1. And doesn't it kind of correlate to this distance down here? Which is what? So, gotta take 1 times what to get to 2? Well, 2. So flip that thing and then do what? Dilate by a scale factor of 2. Okay. Guys, I think we're on to the last example already. Is that true? Or McGurd? Okay. Guys, it says prove that square ABCD is similar to square EFGH. Square ABCD with side length S. Okay. Well, guys, if this side from C to D is S, what's true about all the distances in the smaller square? Aren't they all? Okay. If all the sides in the big square are I'm sorry, if G to H is 2S, what's all true of all the sides in the big square? Okay. So guys, to prove that these are similar squares, we got to show that the ratio of all sides are the same. Okay. First thing I'm going to talk about here is angles. Okay. Guys, what's going to be, if they're squares, what's going to be true about all angles? They're all 90 degrees. So all angles in each square are 90 degrees, indicating same shape, right? Okay, and aren't all squares the same shape? Okay, they just might be a different what? Okay, so that's the thing that we need to do then is this. We need to talk about some side stuff right here. Guys, here's what I'm going to do. I'm going to compare some ratios. Guys, what does AD appear to... All right, let's start with AB. What would AB match up with? EF? I'm going A to B. E to F, right? What would B to C match? FG? How about C to D? What would that match, kids? And how about finally D back to A? What would that match on the other one? Okay, quick question, kids. Okay, all of these sides up top are coming from which square? Smaller one or what? Smaller one or bigger one? Okay, and what are the sides of all of those up there? So I could say this is equal to S over, how about all the sides I listed in the bottom of each ratio or comparison for side by side? They come from the bigger square, don't they? Which have lengths all what? You guys agree that this is 1s over 2s? Okay. So 1s over 2s would be what? You agree that the ratio from AB to EF is 1/2? The ratio of BC to FG is what? Wouldn't that be 1/2 also? C to D would be compared to GH. What ratio would that be? Wouldn't that be 1/2? Anybody want to guess what the ratio of DA to HE is? Guys, what have I done right here? I've shown that the corresponding sides have ratios that are all the same. Okay, aren't the ratios of all the sides, or aren't the ratio of corresponding sides the same? So here's the deal. Ratios of corresponding sides are the same. Over here, I'm going to say corresponding angles are the same. Okay. If you can show that corresponding angles are the same and corresponding side ratios are the same, then what must be true about the figures? So here's what we're going to say. They're going to be similar then, right? Same shape, different size. Here's what we're going to say, and this is probably going to be true for everything, okay? We're going to say square ABCD is similar to square, what's the other square that they're looking at? EFGH, because corresponding angles are equal and corresponding side ratios are what? Corresponding side ratios. Did it just kill out up there? Or is it still writing? Okay. Guys, this is really what you want to say almost for every proof. When they say, are they similar? You need to show that the corresponding angle measures are the same. That keeps the shape the same. But then you want to show the corresponding side ratios are the same. That's your dilation, okay? Guys, one square is half the size of the other one by side length, isn't it? That's what we're trying to show for most of these here, okay? So guys, a pretty quick section here this morning. What questions do you have for me right now? A similarity transformation. Do some moves, but at some point a dilation happens to change the size. You keep the shape, but you're changing the size, and that's the stuff we're working on today, okay? All right, kids, here's what I need from you today, or here's what I'm going to request of you. First of all, I'm just going to tell you, I sent out a big ideas, started in that today. I think that would be a good idea. What did I do here?